Practically speaking, a solution that is considered a buffer is one which contains both a weak acid and its conjugate base. For a solution to be considered a buffer, the ratio of acid to conjugate base, or conjugate base to acid, should not exceed 10 to 1. Understand that the conjugate base always has a counter ion, usually sodium, but potassium is also common. This metal counter ion has no effect on pH and can be ignored for practical purposes in buffer problems. Make sure you understand that, for example, the acetate ion, for all intents and purposes, is the same as sodium acetate. Here are some typical solutions: acetic acid and sodium acetate, hydrofluoric acid and sodium fluoride, nitrous acid and sodium nitrite. Buffer solutions are typically made 3 different ways. One method involves mixing a solution of weak acid with a solution of its conjugate base. For example, mixing a solution of acetic acid with sodium acetate. Another method involves adding a strong base to a weak acid. The strong base will react completely with the weak acid, so in order to create a buffer, the amount of base added cannot exceed the initial amount of weak acid present. Remember, the ratio of weak acid and conjugate base must be within the 10 to 1 mole ratio in order for the solution to be considered a buffer. In this example, initially we have a solution containing 0.010 moles of weak acid. The solution is then treated with 0.005 moles of sodium hydroxide. The hydroxide reacts completely with the weak acid and is fully consumed. The weak acid that reacts with the hydroxide is converted to the conjugate base. Adding an appropriate amount of strong acid to a weak base also creates a buffer solution in what is essentially the reverse of the previous example. Remember, for a solution to be considered a buffer, the ratio of acid to conjugate base cannot exceed 10 to 1. In the context of a titration of a weak acid with a strong base, the buffer region is the area where some of the weak acid has been converted to its conjugate base and there is an appreciable amount of both weak acid and conjugate base present. This is an area before the equivalence point has been reached. So in this example, initially there is only weak acid present in the solution. As strong base is added, the weak acid is consumed and converted to its conjugate base. At the equivalence point, all the weak acid has been fully consumed. The buffer region is where the weak acid and its conjugate base are both present. Now let's look at a problem in context. In this problem, we are adding 25 milliliters of sodium hydroxide to 40 milliliters of a weak acid. In order to calculate the resulting pH, we must first analyze the facts. A strong base is being added to a weak acid. If the acid is completely consumed, the resulting solution will be basic. If the acid is not consumed, the resulting solution will contain both weak acid and conjugate base, and therefore most likely be a buffer solution. To start the problem, we need to calculate the initial number of moles of weak acid and then calculate the number of moles of strong base that will be added. Multiply concentration by volume in order to calculate moles. Typically, a table is used in order to visualize the reaction mathematically. Initially, there is only weak acid. Strong base is then added, which reacts with the weak acid, producing conjugate base. Since the amount of strong base added is less than the amount of weak acid initially present, the strong base is fully consumed and the final solution contains both weak acid and conjugate base. At this point, the Henderson-Hasselbalch equation can be used to calculate the pH of the buffer. The equation is simply a mathematical rearrangement of the expression for Ka, which states that pH equals pKa plus log of the ratio of conjugate base to weak acid. Take the negative log of the given Ka in order to calculate the pKa. Once the pKa has been calculated, simply use the moles of both conjugate base and acid present in order to calculate the final pH. Instead of using the Henderson-Hasselbalch equation, the pH can be calculated by analyzing the equilibrium that exists between the weak acid and its conjugate base. In order to do so, we must first calculate the concentration of both. Simply divide moles by total volume in order to calculate the concentration. Remember, we added 25 milliliters of base to 40 milliliters of acid. An IRE table is usually employed to visualize the equilibrium mathematically. As usual with a weak acid, which has a small Ka, we can assume X, or the amount of acid that ionizes, to be small. Assuming X is small, we can simply use the Ka expression in order to calculate the hydronium ion concentration and finally the pH. As you can see, the result is the same whether using this method or the Henderson-Hasselbalch equation. To verify the validity of our assumption that X is small, we must compare X to the initial concentration of weak acid. If the X to weak acid ratio is less than 5%, the assumption is valid.